This is a short introduction to the software demonstration entitled Nonlinear Mixed Effects Modeling of Deterministic and Stochastic Dynamical Systems in Wolfram Mathematica. Nonlinear Mixed Effects Modeling, or NLME modeling for short, also known as population modeling, addresses the situation when data is collected from a group of subjects. A common model structure is considered, but one or several parameters in the model is assumed to vary from subject to subject. On this slide, we see a pharmacokinetic pharmacodynamic example with joint input-output data for measured drug concentration and drug effect over time. The model consists of three compartments where drug concentration drives the drug effect R, modeled as a first-order linear system with input saturation. The observed inter-individual variability in the time series is here assumed to stem from differences between subjects in drug clearance, denoted CL individual, and drug effect baseline E0 individual, that is steady state level without drug. Here to the left, the full dynamical system population model is shown. The population model is given in terms of fixed effects, which are parameters that are the same across all individuals, and normally distributed random effects, modeling the inter-individual variability. To the right, the corresponding formulation using the NLMEModeling Mathematica application. The notion follows the standard syntax for ordinary differential and algebraic equations and expressions in Mathematica. We load the package, import the data, state the system equations and observation expressions, state measurement noise covariance matrix, a call to the main function NLME dynamical model fit, including start parameter values, symbols used for random effects, and covariance matrices. The result is a fitted NLME model object containing a substantial amount of information. The fitted NLME model object can be asked for the model summary, containing information about estimated parameter values, standard errors, etc. Model evaluation can be performed using the command goodness of fit analysis, generating diagrams for observation prediction comparison and residual analysis. A common way to evaluate model quality in NLME modeling is by investigating the statistical properties of the so-called empirical base estimates of the random effects. Another model evaluation tool is so-called visual predictive check. Now, consider the case of stochastic dynamics, where we introduce system noise in terms of Gaussian white noise signals, effectively turning the ODEs into SDES. To the left, the full dynamical system population model is shown, and to the right, its corresponding formulation using the NLMEModeling Mathematica application. Note the minor adjustments needed to specify the use of stochastic dynamics. The call to the main function NLME dynamical model fit now includes also symbols for the Gaussian white noise signals and corresponding additional parameters with start values. The model summary of the fitted model objects now also contains information about the size of the system noise, here given by G. Functions for model evaluation works also for stochastic dynamics, for example, visual predictive check. NLME modeling covers functionality for continuous time dynamical systems with discrete time observations for parameter estimation, model evaluation, data generation, and visualization. The development of NLME modeling has been performed at the Fraunhofer-Chalmers Center for Industrial Mathematics in Gothenburg, Sweden, involving a number of talented persons. The application is freely shared on request through our homepage.